Modern software development prioritizes speed. Engineering teams are constantly pressured to ship features faster and deploy updates instantly. But moving at that pace introduces a massive vulnerability. One unverified line of code can bring down an entire system. To survive in this environment, systems have to treat every new addition as a potential threat. Every single commit must be considered hostile until it proves otherwise. This is the Educonnect architecture. It replaces blind deployments with an automated validation framework. Before reaching production, software is forced through a security gauntlet. Pushing to GitHub doesn't launch an application. Instead, it triggers a layered validation process, testing the code from multiple angles. The logic behind this pipeline is entirely rigid. Every individual check has to pass. If one fails, the entire process halts. Enforcing this strict sequence is the only reliable way to maintain high development velocity without sacrificing the integrity of the broader network. The first barrier in this gauntlet is static application security testing, or SAST. At this stage, the pipeline scans the code as raw, uncompiled text. Automated scanners, like CodeQL, read through the repository hunting for structural flaws. They look for hard-coded secrets, weak cryptography, and SQL injection vectors that human reviewers might miss. This interface shows the system evaluating the code for poor structural practices. Look at this highlighted vulnerable regex pattern in the SonarQube interface. Because these patterns can cause excessive CPU loops, identifying them early prevents potential denial of service attacks in production. The enforcement here is physical. A developer cannot merge their pull request until this quality gate passes completely. Neutralizing these structural flaws at the source prevents both the exposure of sensitive data and the catastrophic resource exhaustion that halts live services. Once the raw text clears the first gate, it is packaged into an immutable Docker container. This guarantees the software environment remains identical across every stage of testing and production. But containers introduce a new vulnerability, the software supply chain. Relying on third-party base images and language dependencies means you risk inheriting known flaws straight from the internet. This terminal readout shows a Trivy scan targeting an unhardened Node.js base image. The scanner found 1 critical and 21 high-level vulnerabilities buried in the operating system packages. Compare that to this scan of a hardened container using a lightweight Alpine base image. By actively reducing the attack surface, the scan returns 0 critical findings. Hardening the container ensures the engineering team is building their architecture on verified bedrock, rather than deploying pre-compromised infrastructure. The final barrier before deployment treats the infrastructure itself as software. Using infrastructure as code, the actual server environments are defined by text files that must be audited. This Infrascan report card shows the pipeline catching a dangerous misconfiguration. Before a single server spins up, the system flags that leaving SSH access exposed to the open internet is a security violation. With the infrastructure secured, the code moves to an isolated Kubernetes cluster. Here, the backend, frontend, and database pods are spun up for a final aggressive test. This is where dynamic application security testing begins. Tools like OWASP ZAP attack the live running application, exactly as a real-world threat actor would. Dynamic testing actively hunts for runtime injection attacks, authentication flaws, and exposed endpoints that static text scanners simply cannot see. Bridging the gap between theoretical safety and actual runtime durability provides the final proof required. Only after surviving this phase does the code earn its deployment to production. Reaching production is not the end of the process. Once the application is live, it enters a state of continuous telemetry. This Grafana dashboard captures observability layers, actively monitoring the Kubernetes cluster for behavioral anomalies. Here, a triggered alert is notifying the team of sudden, unexplained CPU usage spikes. If you cannot measure the system's live behavior, you are entirely blind to emerging zero-day threats. But automated dashboards, rigid testing gates, and strict pipelines are only as effective as the engineering culture that interprets and acts on the data. By enforcing discipline over velocity, the Educonnect pipeline ensures that every deployment is rigorously verified, heavily monitored, and built to survive.